It is indeed true that a regular ohmmeter will not read ground resistance accurately. Ohmmeters measure resistance between 2 points. In the case of ground resistance, one point is the test ground, and the other point is typically a known good ground or a reference electrode buried in the earth. However, ohmmeters inject a test current into the ground, which can create stray currents that affect the overall resistance measurement. This can lead to inaccurate readings, especially in high-resistance ground conditions. Ground resistance meters are specifically designed to measure ground resistance accurately. They use a 4-terminal Kelvin sensing method to eliminate the effects of stray currents. The 4 terminals include true current terminals and true voltage terminals. The current terminals inject a known current into the ground, while the voltage terminals measure the voltage drop across a known resistance. The meter calculates the ground resistance by dividing the voltage drop by the current. This method is much more accurate than using an ohmmeter. Ground resistance meters are more complex than ohmmeters. They require specialized circuitry and components to achieve accurate measurements. They are also designed to withstand harsh environments such as moisture, dirt, and extreme temperatures. In addition, ground resistance meters are often calibrated to meet specific standards, which adds to their cost. If you require accurate ground resistance measurements, it is highly recommended to use a dedicated ground resistance meter. While ohmmeters may provide general resistance readings, they are not suitable for precise ground resistance measurements. The high cost of ground resistance meters can be justified in applications where accuracy and safety are critical, such as electrical system safety, lightning protection, grounding of electronics, and testing of electrical equipment. To further understand the differences, let's delve into the principles behind each type of meter and the challenges involved in measuring ground resistance. An ohmmeter, in its simplest form, works by applying a known voltage across an unknown resistance and measuring the resulting current. Using Ohm's law, resistance equals voltage divided by current, the meter then calculates and displays the resistance value. This method works well for measuring the resistance of discrete components like resistors, but it runs into problems when trying to measure ground resistance. Ground resistance is the resistance encountered by electrical current as it travels through the earth. Unlike a resistor, the earth is not a homogeneous conductor. Its composition varies depending on soil type, moisture content, temperature, and the presence of minerals and other substances. These variations cause the resistance to change from one location to another and even at different depths in the same location. Furthermore, the earth is a 3-dimensional medium, and current can spread out in all directions, making it difficult to define a clear path for the current to follow. When an ohmmeter injects current into the ground, the current doesn't flow in a straight line between the 2 test points. Instead, it spreads out through the soil, creating complex current paths. These stray currents can interact with other conductive objects in the vicinity, such as buried pipes, metal fences, or even the grounding systems of nearby buildings. These interactions can distort the current flow and affect the resistance measurement. Another factor that affects the accuracy of ohmmeter readings is polarization. When a direct current flows through the soil, it can cause a buildup of ions at the electrode-soil interface. This buildup creates a polarization voltage that opposes the flow of current, effectively increasing the measured resistance. The effect of polarization is more pronounced when the soil is dry or has a high resistance. Ground resistance meters overcome these limitations by using a more sophisticated measurement technique called the 4-terminal Kelvin method, also known as the 4-point method. This method eliminates the effects of lead resistance and straight currents, providing a more accurate measurement of ground resistance. The 4-terminal Kelvin method uses 4 electrodes instead of 2. The outer 2 electrodes, called the current electrodes, inject a known current into the ground. The inner 2 electrodes, called the potential electrodes, measure the voltage drop caused by the current flow. The key to this method is that the potential electrodes are placed within the current path, but they do not carry any current themselves. This eliminates the effect of lead resistance, which can be significant when measuring low resistances. The voltage measured by the potential electrodes is directly proportional to the ground resistance between them. The meter calculates the ground resistance by dividing the voltage drop by the known current. Because the potential electrodes do not carry any current, they are not affected by polarization or stray currents. This makes the 4-terminal Kelvin method much more accurate than using an ohmmeter. Ground resistance meters also use alternating current instead of direct current. Alternating current eliminates the effect of polarization as the polarity of the current reverses periodically. The frequency of the alternating current is typically low, such as 50 Hz or 60 Hz, to minimize inductive effects. In addition to the 4-terminal Kelvin method, ground resistance meters often incorporate other features to improve accuracy and reliability. These features may include automatic ranging, which automatically selects the appropriate current range for the measurement, and filtering, which reduces the effects of noise and interference. Ground resistance meters are also designed to be rugged and durable. They are typically housed in waterproof or weatherproof cases to protect them from the elements. They are also designed to withstand vibration and shock, which can occur during field use. The calibration of ground resistance meters is also an important factor in their accuracy. Ground resistance meters are typically calibrated to meet specific standards, such as those published by the Institute of Electrical and Electronics Engineers, known as the IEE, or the International Electrotechnical Commission, known as the IEC. These standards specify the accuracy requirements for ground resistance meters and the procedures for calibrating them. The calibration process involves comparing the meter's readings to known resistance standards. If the meter's readings are not within the specified tolerance, the meter is adjusted until it meets the requirements. The cost of ground resistance meters reflects their complexity, accuracy, and durability. They require specialized circuitry and components to achieve accurate measurements. They are also designed to withstand harsh environments and are often calibrated to meet specific standards. While ohmmeters can provide a general indication of resistance, they are not suitable for accurate ground resistance measurements. Ground resistance meters are the only reliable way to measure ground resistance accurately. Accurate ground resistance measurements are essential for ensuring the safety and reliability of electrical systems. A low ground resistance is necessary to provide a path for fault currents to flow back to the source, tripping circuit breakers and protecting people from electric shock. A high ground resistance can prevent fault currents from flowing, increasing the risk of electric shock and equipment damage. Ground resistance measurements are also used to verify the effectiveness of grounding systems. Grounding systems are designed to provide a low resistance path to ground for electrical current. They are used to protect people from electric shock and to prevent equipment damage. Ground resistance measurements can be used to identify problems with grounding systems, such as corroded connections or broken conductors. In addition to safety, ground resistance measurements are also important for the proper functioning of electronic equipment. Electronic equipment is often sensitive to voltage fluctuations and noise. A good grounding system can help to reduce voltage fluctuations and noise, improving the performance and reliability of electronic equipment. Ground resistance measurements are used to ensure that grounding systems meet the requirements of electronic equipment manufacturers. There are several types of ground resistance tests that can be performed, each with its own advantages and disadvantages. The most common types of ground resistance tests are the fall-off potential test, the soil resistivity test, and the clamp-on ground resistance test. The fall-off potential test is the most accurate method for measuring ground resistance. It involves driving 2 auxiliary ground rods into the earth and measuring the resistance between the test electrode and each of the auxiliary ground rods. The fall-off potential test is typically used for measuring the ground resistance of large grounding systems, such as those used at power plants and substations. The soil resistivity test is used to measure the resistance of the soil. It involves driving 4 electrodes into the earth and measuring the resistance between them. The soil resistivity test is used to determine the optimal location for grounding electrodes. The clamp-on ground resistance test is a non-invasive method for measuring ground resistance. It involves clamping a clamp-on meter around the ground conductor and measuring the current flowing through the conductor. The clamp-on ground resistance test is typically used for measuring the ground resistance of individual pieces of equipment. When choosing a ground resistance meter, it is important to consider the following factors: accuracy, range, resolution, features, and durability. Accuracy is the most important factor to consider when choosing a ground resistance meter. The meter should be accurate enough for the application. Range is the range of resistance values that the meter can measure. The meter should have a range that is appropriate for the application. Resolution is the smallest change in resistance that the meter can detect. The meter should have a resolution that is high enough for the application. Features are the additional features that the meter offers, such as automatic ranging, filtering, and data logging. The meter should have the features that are needed for the application. Durability is the ability of the meter to withstand harsh environments. The meter should be durable enough for the application. Ground resistance measurement is a critical aspect of electrical safety and system performance. Understanding the limitations of standard ohmmeters and the advantages of dedicated ground resistance meters is essential for anyone working with electrical systems. The investment in a quality ground resistance meter is justified by the increased accuracy, reliability, and safety it provides. Let's consider some specific applications where accurate ground resistance measurements are crucial. Firstly, in electrical system safety, a low ground resistance ensures that fault currents can quickly flow back to the source, tripping circuit breakers and preventing electrical shocks. This is particularly important in environments where people are likely to come into contact with electrical equipment, such as homes, offices, and factories. Secondly, lightning protection systems rely on low ground resistance to effectively dissipate lightning strikes into the earth, preventing damage to buildings and equipment. Regular testing of ground resistance is essential to ensure that these systems are functioning properly. Thirdly, the proper grounding of electronics is essential for preventing damage from electrostatic discharge and other electrical disturbances. Accurate ground resistance measurements are needed to verify that grounding systems meet the requirements of sensitive electronic equipment. Fourthly, when testing electrical equipment, ground resistance measurements are used to ensure that the equipment is properly grounded and that there are no faults in the grounding system. This is particularly important for high-voltage equipment, where a fault in the grounding system can be life-threatening. In summary, while a standard ohmmeter might seem like a convenient tool for measuring ground resistance, its limitations make it unsuitable for this purpose. Ground resistance meters, with their specialized design and 4-terminal Kelvin sensing method, provide the accuracy and reliability needed for critical applications. The higher cost of these meters is justified by the increased safety and performance they provide. Remember that electrical safety is paramount, and investing in the right tools is essential for protecting people and equipment. When working with electrical systems, always follow proper safety procedures and consult with qualified professionals when needed. By understanding the importance of accurate ground resistance measurements and using the appropriate tools, you can help to ensure the safety and reliability of electrical systems in a variety of applications. The accuracy of a ground resistance measurement is affected by several factors, including the type of soil, the moisture content of the soil, the temperature of the soil, and the presence of buried metal objects. Different types of soil have different resistivities. For example, sandy soil has a higher resistivity than clay soil. The moisture content of the soil also affects its resistivity. The more moisture in the soil, the lower its resistivity. The temperature of the soil also affects its resistivity. The warmer the soil, the lower its resistivity. Buried metal objects can also affect the accuracy of ground resistance measurements. These objects can distort the flow of current in the soil, leading to inaccurate readings. There are several things that can be done to improve the accuracy of ground resistance measurements. One is to use a ground resistance meter that is designed for the specific type of soil being tested. Another is to take measurements at different times of the year, when the soil moisture content and temperature are different. Another is to avoid taking measurements near buried metal objects. It is also important to ensure that the ground resistance meter is properly calibrated. A properly calibrated meter will provide more accurate readings. Ground resistance testing is an important part of electrical safety. By following proper procedures and using the right equipment, you can ensure that electrical systems are properly grounded and that people are protected from electrical shock. Electrical codes and standards provide guidelines for grounding electrical systems. These codes and standards are designed to ensure that electrical systems are safe and reliable. It is important to be familiar with the electrical codes and standards that apply to your area. These codes and standards can provide valuable information about grounding requirements. Grounding is a critical aspect of electrical safety, and it is important to take it seriously. By following proper procedures and using the right equipment, you can help to ensure that electrical systems are properly grounded and that people are protected from electrical shock.